Continuing on, I'd like to make a couple of early observations that'll help us as we continue to navigate the Rubik's Cube. And one of the things that's most important to notice is that when we're manipulating the cube, the order in which we perform our moves matters. So what I have pictured for you here is starting with our cube in its original position. If we first do an upper move and then follow that with a right hand move, you have this configuration of the cube right here. However, if you start with the cube in its original notation and you perform a right move followed by an upper move, you'll get this configuration of the cube right here. So you have to be very careful in both the order in which you do things and the order in which you undo things on the cube. In general, there's a rule that if you perform a sequence of moves, say you were to turn the upper face of the cube followed by the right face of the cube, and all of a sudden you had a moment of panic and you wanted to go back to the original state of the cube, one thing you should do is reverse those moves, undo them with counterclockwise rotations, but in the backwards order in which you did them. So for example, to undo an upper turn followed by a right turn, what we ought to do is do a counterclockwise right turn followed by a counterclockwise upper turn, and that will return us to our original location. However, there is a little bit of something special going on here because every now and again we get lucky and the order in which we do things on the cube does not matter. And figuring out precisely when this happens is really important to us. So here is a very understandable example with these basic motions that we're doing. If I were to first do an upper move on the cube followed by a down move on the cube, I will actually get the same answer as if I would have first done a downward move followed by an upper move. And really the reason that this works out is because these two motions affect totally disjoint sets of cubies on the cube. And a cubie is one collection of these little cubes. On the larger cube, we tend to use the word cube for the big cube and QB to denote one of these smaller things that is also a cube. Because the cubies affected by the upper turn are totally different than the cubies affected by the downward turn, we can do those moves in either order and get the same outcome. And that's a very special thing. And so that's something we'll be trying to mimic in other motions that we will study. Now here's an amazing thing about the Rubik's Cube that is also very helpful. So we went over earlier, if I had done an upper turn followed by a right turn and I wanted to undo that, one way that I could undo that is by reversing the right turn and then reversing the upper turn. But if you get lost in a sequence of moves and don't want to think through how to backtrack in that particular way, any collection of moves that you do on a Rubik's Cube can be undone if you just repeat them enough times, which is amazing. And in fact, a lot of algorithms for solving Rubik's Cubes use that mentality. So for example, I've shown in the first frame here the sequence of moves R2, U2, where what I mean by that is turn the right face twice and then the upper face twice. If I do that one time, the cube will look like this. If I do that 2 times, the cube will look like this. But if I go ahead and I do that 3 times, I'll get back to my original position. And so a lot of algorithms for solving the Rubik's Cube rely on you finding the cube in a particular frame and saying, if it looks like this, if you picked up the cube and it looked like this, I don't know how many times you'll have to do it, but do this sequence of moves and just do it until the cube is fixed. And so you'll find some algorithms for cube solving that use that mentality. What's more is that the number of times we might have to do something is not actually a mystery if we go back and return to that tabular method of keeping track of the stickers and what number it's mapped where. Then it's not a matter of just do this motion until it's back to the original location. It's more of a, I can tell you exactly how many motions that's going to take. And that's a little bit more powerful because there's a website you can go to. It's a really interesting website that lists a whole bunch of numbers of times for specific moves that you'll have to do them. And some of them you might need to do something like 60 times. That's not a very helpful thing. But if I knew it were going to be 60 right away, I might not be willing to invest in learning that algorithm. And what we're going to do is discuss something called the order of a motion of the cube. And that's the number of times that you would have to do that motion to return it to its original state. And we want to do that for the first time. So it's true, for example, that I could take the right turn and I could turn the right side of the cube 16 times and it would be back to where it started. But we're going to define the order of that right-hand turn to be 4. And in fact, the order of any turn is going to be 4 because 4 is the smallest number of times that I have to turn it until it's back to its original state. For a slightly different example, that R2U2 turn that we did on the previous page has an order of 3 because the first 2 times I did that motion, I got cubes that were jumbled up, but as soon as I hit that 3rd time, I was back in my original state, and that was the first time that that had happened. Now, what we'll start to cover in the next video is this mechanism we have for determining precisely what the order of a move is, and we're going to determine that from what's called the cycle structure of that motion, and that's going to be born out of the tabular notation that we considered previously, but that will be the subject of our next video.